Ever since Microsoft introduced generics into the language, they have been used almost everywhere. Even if you don't understand how they work, using generics is very easy. In this video, we're going to look at why generics are important and then how to create them. We'll look at the different types of generics, how to limit generics, and how to implement some of the more recent generic types, such as generic interfaces and numeric generics. Now, this video is a standalone training video that will teach you a specific coding topic. Every Monday, I provide videos like this. On Thursdays, I release podcast videos that cover the topics software developers need to know that don't include writing code. If you're looking for a sequential training on a topic with a real-world focus, you can check out IamTimCorey.com, where I have dozens of courses meant to prepare you to be a software developer. If you're just getting started, check out the master courses. Those courses are designed to start you at the beginning and get you job ready by the end. Okay, let's jump over to Visual Studio, and we're going to create a new console application. Very generic, very quickly and easily. We're going to try to avoid all of the UI stuff, so a console application is the way to go. This will allow us to demo just generics and not anything else. So we'll call this generics demo and generics demo app. And I'll put this in my temp folder. Next, we'll hit, we'll see that it's .NET 8. Yes, that's what we want to use. We're using Visual Studio 2022, the latest version. So this is all as of .NET 8. So if you're using .NET 9 or .NET 10, if you're in the future, cool. It'll probably still all work the same, even if you choose the later versions. But we are going to use top-level statements, and we're not going to worry about AOT. Okay, once this gets created, we'll get rid of the initial entry here, and I'll put a few empty lines here. So what we're going to do is we're going to look at what generics are first and why they're important. And probably the most common way of doing this is looking at what we have for generics today. So we have a list of what's called T. T is the representation of a generic, meaning you can put any type you want in here. So we could say list of int. We could say numbers, and we could instantiate that and then start using it. We could say, we could even instantiate it right away. This is a newer feature. We're going to say, 1, 2, 3, like so. And now there's 3 numbers in this list, and they're all integers. And this is different from saying list of string, where we might say strings equals, and we'll say Tim and Corey and Sue. Okay, so there's 3 strings there, and strings, as we know, are different than integers. And if we try to say something like this, well, that's not going to work. You get a red squiggly. It says, no, you can't convert an integer to a string implicitly. So we could, in theory, do something like toString, but what it's saying is, I'm expecting you to put a string here, but you're giving me a number. But yeah, up here, we can put numbers, no problem. So if I put 4, that works. Well, why is that? Because we're using generics, and what generics allows us to do is specify the type. And then only that type will be used. We have what's called type safety, meaning if you put the wrong type in there, the compiler at design time can yell at you and say, no, you can't do that. That's the wrong type, even though we can have different lists with different types. So that's one of the benefits here of generics. But you might say, well, Tim, we could do this before that. We could do something like this, where we could say, and please don't ever do this, but I'm going to demonstrate why you shouldn't do this. So list of object, because really everything derives from object, right? So I could say list of objects called objects, and I could then go, well, Tim and 4, and that works. So why couldn't we just have one list called list of objects instead of list of T? Why don't we have just objects? Well, the reason why is because this is really not efficient. This is very much not efficient, and it's also not type safe, meaning I could put a different type in here. I could put 3.6, which now that's a double, or I could do a decimal, or I could do, an object like a person model. I could put all these different things in this list of object and it would work. It's just not great. So even if we didn't use generics and we just had one list, and we don't have to specify object then, but there's a list of objects, I'm just simulating what that would look like, that wouldn't be good. And the reason why is because of the fact that behind the scenes, what happens is what's called boxing. And so the way this works is this right here, 4, is a value type. But objects are a reference type, which means that in order to put a value type into a reference type, you have to convert it. You have to wrap it in an object. So you're saying object of 4, not just 4, which means it changes where it is located in memory, and it is an expensive operation to box and unbox this value. I can do a quick example for you just to show you how this works. We could do a stopwatch, which that's under the using system.diagnostics. We'll call it SW equals new. And we're going to do something really basic here. We're going to start the stopwatch, and we're going to have a for loop. And we're going to say 4, 1, 2, and I'll put the underscore here so you can more easily read it, for 1 to 1,000,000. And if you're not familiar, the underscores are just there for visuals. So I could just put 1 and then 6 zeros, it would be just the same. But this way it allows you to see that, yes, this is 1,000,000. And what we're going to do is we're going to say objects.add I. Okay, so we're going to add a number of integers to this objects list. And then what we'll do is say stop the stopwatch, and we'll say console write line, and we'll do a string interpolation and say list of object elapsed time, and then we'll say stopwatch.elapsed milliseconds. And I'm doing 1,000,000 just to be very clear of the differences in time. You wouldn't see much of a difference in a few, but this is to kind of show you underlying that something is different and something has changed. So that's using this. I'm going to duplicate this again and do the exact same code, but this time instead of objects, I'm going to add it to numbers. And so a list of int. And how long is that going to take? So let's just run this and see the difference between these two interactions. So again, same interaction. We're going to create a stopwatch. We're going to start it. We're going to add 1,000,000 objects to our list of objects. And we're going to say, how long did that take? And then we're going to start over again and add 1,000,000 integers to the numbers list. And then say, how long did that take? Just to show why generics is such a good thing. So let's bring us over here, and it took us 57 milliseconds. I should have put the M at the end, but 57 milliseconds to add to our list of objects, where it took us 4 milliseconds to add to our list of integer. And that's just adding to a list. And we're still using really generics, but we're kind of simulating this not being a generic list. So it's much more expensive to do it this way with a list of objects. That's why the generics were created, because we can do things like list of integer. And not only do we get the type safety of saying we can only put integers in here, but we also get the compile time checks to make sure that we're obeying that. And we get no boxing or unboxing when we put those values in. So there's a lot of benefits here of doing this. And I'll get rid of our stopwatch code. You can just recreate it if you really wanted to. But that allows it to be much more efficient to have this generic list. And you're like, cool, I get it, but why would I ever create a generic? And that's valid. There are times when generics are useful. So what we're going to do is we're going to show off how you can create generics, and then we'll touch on a few times when they might be useful. If you ever watched me work with Dapper for data access for C#, I use generics in there to send parameters to and from Dapper. So that's when I would do it a lot, but we'll show a few different times we could do this. So I create a method here called type checker. And what type checker will do, we'll say type checker of type T. So we're specifying here a generic and saying T value. Okay, so what are we doing here? Well, first of all, we're saying this method uses generics. How do we know? Because we put the angle brackets and then put the generic identifier here. By default, the name we use, or the letter we use for generics is T. But you don't have to. You can do whatever you want, but that's the common parlance. Just like when we do a for loop and we have an I for the counter. It's a similar kind of thing. We start with T generally. But again, you might see something different. For example, we have a dictionary. You'll see that it's not just T, it's T key and T value. So what they're saying is, hey, there's a key and a value. They could have just said key and value, but that would have been a little confusing because, wait, is that my value and my key? No, it's a type of your key and value. So instead they said T key and T value. You could do that. You could also do another letter. Typically, if you have a second one, we'll see in a little bit, you'd use a U. But for our case, we're just going to use T. And then we can use that as a type. Pretend this is one type to kind of help visualize this. So type checker of type string, we'd say string value. Type checker of type int, we'd say int value, and so on. So our type checker, we're going to do something really simple here. We're going to say console write line type of T. And that's going to give us the type that we passed in. Not the value, the type. We can also then pass in the value to print out as well. So we could even say something like type, and then do the same thing here for value. I could have done string interpolation, but this is just the same pretty much. So now what we could do is we could call this, let's even get rid of these, and we're going to say type checker and we'll pass in a value of 1. And then we'll do type checker, and we'll pass in a value of Tim. Okay, so there's a couple of different type checkers we're going to run. Each of them will print out something. So we run this, and we get, wait for it to come over here. It's not cooperating. There we go, finally. So we have the type is system.int32, the value is 1. The type is system.string, and the value is Tim, which is interesting because we just passed in the values. We didn't pass in and specify a type. It just knows what that type is going to be. If we pass in 1.1 and we run this again, we can see that the type is system.double and the value is 1.1. So it knows based upon what we've passed in what that type is. And we could be, more specific if we wanted to. We could say something like, how about record, person record, string first name, string last name, right? And they can say here, type checker and new person record, Tim Corey. Okay, so now we're doing a type check on a person record. And it's going to work in the same way, where we have the type person record. It knows it's a person record, and the value is person record, first name equals Tim, last name equals Corey, because records print off really nicely. Now, if we did a class, that would be just a class name, unless you modify the toString. So that allows us to have one type checker method that takes in any type and tells you what that type is and the value of it. So you pass in any value you want, and it goes, oh, that's a double, that's a decimal, that's a person record, whatever the type is, and also what the value is. That could be useful if you're logging something. Maybe you log both what the type is as well as the value of that type. There's lots of different ways to use this, but this allows you to create one method that does this. Now, the comparison would be to have something like void type checker for string and say string value and do that work. And then have another one that you do that is for int. But then when you have something like person record, you got to create another one. But what if you don't know that person record is going to be created? You could put this in a library somewhere, and it wouldn't even matter if you knew what the types were when you created it, because the caller could pass in a brand new type. It's okay. It will figure it out and tell you what that type is. So there's lots of ways you could use this that allow you to not even care about future usage, because it will just handle future usage just fine. Now, that works for methods. We've seen how to use a method now, but let's create a class. I'm going to create a new file for this, just so we don't want to clutter things up. And we'll call this the better list class. All right, and we're going to clean some stuff up here. We'll get rid of all that and make this public. Okay, so this is the better list class, and I'm going to make this generic. I'm going to say better list of type T. And why would a class need a type T? Well, because we're going to use that type T throughout the class. And in this case, what I'm going to do is I'm going to have a private list of type T called data equals new and instantiate that. And you might say, well, Tim, I've never seen that done before. Usually you have to put the actual type there. And I did. I'm saying this type. So it's a little confusing because I've used T and we have list of T. But if I said something like T value, then I'd put T value here. Okay, so that's where the using a T all over can be a little confusing. But in this case, I've passed in a T to the class. And I said, create me a list of T. So I've instantiated a list based upon that type. So it's, if I pass an integer here, I'll have a list of integer. If I pass in string, I'll have a list of string. If I pass in person record, I'll have a list of person record in data. Now I'm going to create a public void add to list. And I'll pass in T value. Now, I don't have to say add to list type T because we've already done type T at the class level. So I can say data.add value. And that will add that value to my newly instantiated list. But in this better list, I not only want to add the value to a list, I also want to do a console write line that says value has been added to the list. Okay, so I don't want to just add things to the list. I want to know when things have been added to the list by having this print out and say console write line, this has been added to the list. Okay, so now let's actually create this back over here. We can comment out just these three so we don't have things printing out we don't need to. And we're going to say better list, which is going to create a using directive at the top for me. I'm going to say better list of type int, and let's move that all the way to the top. There we go. I'm going to say better list of type int. We'll say better numbers equals new. So instantiate this class called better numbers. I'm going to say better numbers.add to list. I could have said add to be kind of consistent with the list, but I said add to list to make sure you know it's different. I'm going to say add 5. But I'm also going to say down here, better list, I'm going to say person record. And we'll say people equals new. So instantiate another class instance of better list, but this time with a person record as T. I'm going to say people dot add to list new Tim Corey. Okay, so I've added myself to this list. So two different types of classes. One's an integer list, one's a person record list, but either way, when I run this code, it says 5 has been added to the list, and it says person record Tim Corey has been added to the list. So it knows what's been added to the list, and it knows that each list is uniquely typed. So if I were to say people.add to list 1, it goes, no, that doesn't work because this is strongly typed, and a number, an int, cannot be a person record. So therefore, that doesn't work. You have to add the correct thing to the list. We have design time checking to make sure that we have type safety. Okay, so make sure we're being safe with our types and not just, this is not just a whatever you want to throw in there, you can. Because what happens is when we compile this, it's going to create the person record specific better list. And it's going to create the integer specific better list. And it's only going to allow those things. This is not some kind of dynamic thing where you can throw whatever you want into that. So we have a generic method. We have a generic class. Well, there's another thing we can do. And let's actually create a new file for this. I'm going to call this IMportance. Okay, and this is a nonsensical one in some ways because I'm not going to create great code for it. That's okay. But I want to show off an interface. We can have an interface called IMportance. And this will allow us to create something that is generic on an interface level. So I can say type T. And in here, I can say T most important, TA, TB. And what this will be is this will be a method that returns whichever value you pass in, A or B, that is most important. So you're passing two values of the same type. It'll get back one value that's the more important one. Okay, so now I could create a class that implements IMportance. So we're going to say evaluate importance. Sure, that's a great name, whatever. Whoops, semicolon goes there. And we get rid of our usings, and we make this public. And I could say, you know what? I want to implement IMportance, but I have to give it a type. Importance of what? Well, let's start with an int. Okay, so now I do control dot to implement the interface, and it says, okay, there's the implementation, which is integers for the T values. And how do I compare importance? Well, let's just do an if A is greater than B, return A, else return B. Okay, I could have made that so much simpler, but that's a really simple evaluation where this now implements IMportance of type int. Now, that's a very specific interface. The interface is for IMportance of integer, which is different than IMportance of type string. Notice it's not implemented. I could implement that one as well. Let's do that. And I can say here, let's actually copy this if statement. And we'll just change the A is greater than B. I'm going to say A.length is greater than B.length. Okay, that's, again, nonsensical in the way that I wouldn't see this in necessarily production code because who's really comparing lengths to say which one's more important? But this kind of illustrates for you how you can use an interface that's generic and implement it with different actual types. So you can write one interface, but have it implement multiple different types and allow you to do, really cool things with it. Now, I'm going to show you one of the ways that Microsoft implemented this interface, generic interface, in a little bit. But let's first talk about constraints. So I'm going to close down all these things. Let's create a sample class for now, just to kind of illustrate the different types of constraints. We're not going to try and make it do anything. I just want to show you how to limit constraints. So we're just going to call it a sample class. And in here, let's still clean this up a bit. Make it public. And I'm going to say the class takes in a generic, or is a generic. But I don't want this generic to be just any generic, because maybe there's some things that I do or don't want it to do. So I can give it a few constraints on here to make sure that it is limited. So I can say where t, and I put colon, I can give it a few different constraints. For example, I can say new. And what this does is says this t must have an empty constructor. So when you pass in this, whatever it's going to be for t, it must have an empty constructor. Or you could say, you know what, I want this to be a class. So I want it to be a class and I want to have an empty constructor. Or you can say, you know what, I want it to be a nullable class. So you can also say things like, and notice the commas mean this and this. I could also say that this is a newer one. I can say not null, which is a warning generator that will say, hey, this is null, and it's saying that it shouldn't be null. It's not an error. So we could also specify a base class. So we could say maybe we, better list. So this is either better list of t or one of its descendants, one of its children. So that could be something we do. We can also say this has to implement an interface, IMportance of type t. Okay, so this not only is this t has to implement IMportance, so it has to be then a class or a record or something else that has an interface called IMportance of t, which is the same type as itself, which would be weird. But whatever interface you want it to be, we could also say where t equal, if we're passing in two values, and notice we can do that, say t and u, which would be, this would be one type, this would be another type. We can actually say where t and u are the same. So now these two are the same, or that u derives from t. So maybe this t is a base class and u is a child class. That could be still valid. But you're saying that these two will be, have the same base class, essentially. Well, actually, that u will derive from t. So there's ways you can limit these. There's not, you don't want to limit them too much in a lot of ways, because otherwise, what's the point? So if you just say where t is implements this interface, well, then why don't you just use that interface instead of passing in a generic? There can be reasons, but more often it's, just use the interface instead of trying to make it generic. But you could also say where t equals a specific interface and u is a different interface. That could be possible as well. So there's ways that you can limit these things so that you kind of dial in exactly what you want for these generics. So it's not just, if you say where t is a class and it has a blank constructor, well, then if I come over here into program.cs and I were to come down here and say sample class of type int test, it goes, no, you can't do that because that doesn't work. So oops, and I can say int and int. And it goes, no, you can't do that because this integer must be a reference type in order to use the parameter t. So I go, okay, I want this to be person record. And it goes, no, you can't do that because it must be a non-abstract type with a public parameterless constructor. Okay, fine. So I'm going to come down here and say class person model. And then I'll in here say prop ID. Okay, whatever. So this has one value in here, person model. So if I pass in a person model, it goes, yep, cool, no problem. But if that person model has a constructor where I pass in an integer starting ID, like so, I'm back to an error here because it says, no, must have a parameterless constructor. And I go, oh, okay. So now I got to create another constructor that has nothing, and we're back to good again with this. So this is how you can limit what your generics can do. And I'll just get rid of this, and in this example, we don't need to have it. Okay, so that's how you can limit your generics at the class level or even at the method level. But what we're going to do now is look at how Microsoft implemented something new and look at the iNumber. And it's kind of a fun one. So let's create a new class, and we'll call this math operations just to show off how to use this. So again, clean this up. One of these days, I will create a template for this to make it easier. But what we're going to do is we're going to pass in a type, okay? We're going to say where t is iNumber of t, okay? So when we pass in this t, that t has to be an iNumber, all right? So it's going to check to make sure we can do that, which means now we can say public t add tx, ty, and we can say return x plus y. Well, if we didn't have this, we couldn't do that. Okay, notice the red squigglies. Why? Because we can't add two objects together. What if they're person record? Well, person record plus person record, how does that even work? That doesn't. What if they are Booleans? How do you add Booleans together? Well, technically you can, but that's another thing. So it doesn't know how to do addition on any generic type or every generic type. But if we limit them to say, hey, this has to be an iNumber, well, then we can do things like add, subtract, multiply, divide, and a whole lot more numeric operations. Which means now if we come back over here and we say, you know what, I want to do math operations on type int and say int math equals new to instantiate. I can create this without making it static, but we're not going to. So I can say console write line int math dot add 1 and 4, right? And that's going to give me the value. Let's comment these out here so we don't have any other values. That'll give me the value of 5, right? So let's run this just to see that it actually does give me a value of 5. And there we go. It says 5. Okay, so now what we're going to do is we're going to create another one. We're going to say math operations of type double and say double math. And I can say the same thing. Let's just copy and paste this here. Only I'll say double math here. And we're going to say that these are doubles. And it goes, okay, fine. I can deal with that. And it's still 5. But just to kind of prove, we can say 1.5 and 4.3. And we can run this again. And we get 5.8. So that works, even though this is a double and this one is an integer. And if we were to try and pass 4.3 here, it's not going to work. It's going to say, no, I can't take a double. I need an integer. And we could even change this to say decimal, and it says, well, hey, whoa, you can't do that because these are not these are doubles, not decimals. So we have to pass in decimals there. And I'll just undo that for now. So we could pass in whatever numeric type, doubles, decimals, integers, floats, and so many other things because they all implement the I number of type T. So this allows us to create more robust math libraries. Up until this point, typically what I recommended was that you would create a math library with doubles because that's what Microsoft does for everything. And that's where you can do things like Power and other things that they take in doubles. So if you were to do, math dot and say, look at all the values, notice it takes in a double, it takes in a double, takes in a double, takes in a decimal for that one. But you start looking at all these different things and they take in double, okay, decimal. So what you can do is you can actually create your own math library that takes in whatever values you're using, whatever type you're using, without having to do conversions. That's where the real power of generics comes in, because you're not doing conversions. Yes, if you have two integers, you could convert them to double and then add them together, but then you have to convert them back to an integer, which is expensive to do all of that when you could just add two integers together. And if you have decimals, adding two decimals together is not the same as adding two doubles together. There's a different system there because of the significant digits and all the rest. So you don't want to do conversions back and forth because you could actually lose significant places after the decimal and so many other things. So having this generic allows it to be more specific in how we do things. So that's how generics works. That's why you might use them. I would encourage you, like anything else in software development, use it, don't abuse it. Okay? Don't look for every possible case to use generics, because often you'll find that a class would have done just fine, or an interface, or using an interface will have worked just fine. But when used correctly, generics can make your code much more efficient, much more dry, and much easier to understand and read. So there's a lot of benefits to using generics. We see generics a lot with things like list and dictionary and other things, where these are all generics now because of the fact that it gives us that type safety. It gives us the ability not to box and unbox values and compile time checking and so many other things. We also see that things like logging, where we can just say, hey, log whatever, log this class, log this method, log this value. We don't have to know about specific types, and it can still derive information from the caller and so many other things. So generics are awesome, and when used correctly, they're really powerful. I encourage you to understand them, practice them. It's really important that you practice this stuff. Just seeing it isn't going to be enough. Actually practicing it, trying it out, is really valuable to understand how it works and make sure that you know how you can use it in the future. All right, thanks for watching. And as always, I am Tim Corey.